All right, guys, let's finish up the notes that we started in class. So this is kind of where class ended, right? When we were doing the repeated use of the chain rule. And this is gonna happen on the tests and on quizzes. You will see this, okay? So I'm gonna redo this problem just because it was kind of in the last minute of class. So remember, first thing we're gonna do is we're gonna rewrite it using parentheses. That way we can figure out the composition part of this whole entire thing. So this is gonna be rewritten as secant x over 2, and all of that is gonna be raised to the half. So when you're looking at this problem, remember you're thinking of this blow pop, right? Here, basically what you have is first you have to take off the wrapper of the blow pop. So the outside most function is going to be this half. And then once you get rid of that half, the next part of the function is the secant. And then the last part is going to be this x over 2. So let's take care of that 1/2 first. So pretend that basically what's in here, the secant x over 2, is just one item that's going to come along for the ride. So all of this is raised to the half. So I'm going to bring that half down. So now we're going to have 1/2. All of this is going to come along for the ride. And now, instead of half, it's going to be raised to 1/2 minus 1. We'll clean it up in just a second. But because there is a second function and a third function, the secant and the x over 2 still in here, I need to go ahead and apply the chain rule. So I need to still derive. So then the second part is going to be deriving now the inside stuff. In this case, the second function is secant. The derivative of secant is going to be secant tangent. And it's the secant of this stuff. So secant of x over 2 times tangent of x over 2, right? And that's the derivative of secant of x over 2. Is secant of x over 2 times tangent of x over 2. And then the last part, again, another chain rule, is going to be the derivative of the insidemost function, which is the x over 2. And that's just going to be 1/2. The derivative of 1/2 x, or x over 2, is 1/2. And then, of course, the final step would be to clean it all up. I'm going to multiply that half by that half. I'm going to get 1/4. This is going to be secant of x over 2 raised to the negative half times secant of x over 2 tangent of x over 2. And, of course, the only thing we can't have is negative exponents in math, so we got to bring that guy down. So it's going to be 1/4 square root of secant of x over 2 times secant of x over 2 tangent of x over 2. And that's it. That's our y prime answer. All right, moving on to C. So in C, again, we're going to always try to rewrite it using parentheses so we can identify who's the inner outermost functions. So this is going to be rewritten as cotangent of 3x over 2. All of that is going to be raised to the 2/3. So here we have, if you think of all of the parts of the function, right? Think of plugging in a value for this x. So the first thing that you would do is you would plug it in here and do 3x divided by 2. The next thing you're going to do is take the cotangent of that answer. And then the last thing you're going to do is raise it to that 2/3. So when it comes to the chain rule, we're going to derive this guy first, this guy second, and this guy third. Okay? So let's go ahead and do that. So the first thing I'm going to do is I'm going to bring that 2/3 down. Everything else is just coming along for the ride. And all of that now is going to be raised to 2/3 minus 1 times. Now we're on the second guy, the derivative of cotangent, just cosecant squared. So the derivative of cotangent is going to be cosecant squared of the third stuff. And then the last part is going to be the derivative of 3/2 x, which is just 3/2. And then down here, we're going to clean this up. So y prime is equal to 2/3 times 3/2, which actually does cancel out itself, right? So that 2 and that 2 cancel out because everything's being multiplied, and that 3 and that 3 cancel out. So now you're really just left with 2/3 minus 1, which is going to be negative 1/3. So I'm going to bring that down. So 1 over cotangent 3x over 2 to 1/3. You can rewrite it as cube root of all of this times cosecant squared of 3x over 2. And you can write this part in the numerator right there. It's the same exact thing. So it's identifying how many parts of the composition there are and then undoing those parts using the chain rule. All right, natural logs and exponential functions. So here, we're going to have to recall the derivative of ln of x is always going to be 1 over x. And x has to be greater than 0 because obviously if it is equal to 0, this thing is undefined. And because we need to know that the function of ln of x looks like this, right? It will never ever touch the negative because you cannot have a negative inside of a log, a negative value. So when it comes to the chain rule, if ln has a function inside, it's going to be 1 over that stuff of u times the derivative of du dx. Okay? So a few log properties that you need to remember. ln of 1 is equal to 0. The power property of logs, you remember this? Bringing down the power. And then you can rewrite it as n ln of a. The product property of logs can be separated. If two things are being multiplied, you can separate them into ln of a plus ln of b. And ln of a divided by b can be separated into ln of a minus ln of b. So these will be useful when dealing with natural logs, learning how to rewrite them. So using the chain rule with logs, okay, we're going to call this the stuff, right? And we're going to find the derivative. So ln of stuff is equal to 1 over the stuff times the derivative of that stuff. So when you rewrite it, you got 1 over 2x times the derivative of 2x, which is just 2. And that ends up being 1 over x because the 2's cancel out. Okay? Actually, logs and exponentials are one of my favorites because I think they're the easiest. So in this case, here's the stuff that's inside ln. So when you're taking the derivative, you've got y prime is equal to 1 over all of that stuff times the derivative of that stuff. So when you clean this up, you've got 1 over x squared plus 1 times 2x. And then you can do a little more cleanup by just bringing these two together. All right, next problem. Well, now we've got two functions that are being multiplied together. So we don't just have a chain rule situation right here, but we have a product rule and a chain rule. Or actually, because this is ln, I can do a rewrite and make it so much easier on me where I'm only using chain rule by doing ln of sine of x, and all of that is going to be raised to 2x. Well, the stuff in here is going to be raised to x. So let me do my little rewrite. Okay. So now when you're actually looking at this, so this is a rewrite, the outside most function, and the way you can think of it again is if you were to plug in a value for x, the first thing you would do, and I probably should have put a parenthesis right here, the first thing you would do is do sine of x. And then whatever that answer is, that guy gets raised to that x, right? I'm following PEMDAS. So we start here, raised to x, and then the last part is taking that ln. So when you are applying the chain rule, when you're trying to figure out the derivative, that means you're going to derive this first, this part second, and the sine of x all the way on the inside right here is going to be third. Another way, like I was saying before, you could use the product rule. These are two functions that are being multiplied together. So you could take the first guy as is times the derivative of the second guy, which is 1 over sine of x times cosine of x, plus ln of sine of x times 1. And you would be done, okay? So you only have to use the chain rule right here. So there's two different ways of doing this problem. I'm going to leave this one for you. Let's see how, which way you find easier, and go from there. All right, next up. So here we have a composition function, and the two parts are ln of x, and then it's going to be cubed. So obviously we're going to start on the outside first, and we're going to take the cubed part down. So that's going to be 3 ln of x, and then we're going to times that by the derivative. Oh, I forgot to put the squared there. And we're going to multiply by the derivative of ln of x. So now y prime is going to be 3 ln of x squared times the derivative of ln of x, which is 1 over x, Remember, this guy right here, its derivative is just 1, so I don't really need to write that. Okay, even though we're always doing the chain rule, when the function is just x, we don't need to do that. All right, C. So C is a massive function, right? A lot going on with C. So my rule of thumb is we are going to start on the outside. So we're going to first take that derivative of ln of all of this stuff, right? All this stuff is just going to follow along. So the first part is the derivative of ln, which is 1 over stuff. 1 over all of this. Right? Here's the stuff. And then we're going to multiply that by the derivative of the stuff that's on the inside. But there's a lot going on here. We have quotient rule, we have chain rule, we have product rule. So this is one of those problems that you really need to stay organized for. Just for the sake of time in this video, I would like to leave this problem for us to do it in class together, because this is going to take, it's going to take a minute. Okay, because there are different approaches to it. Just by looking at it, by looking at this, instead of using the chain rule and the product rule at the same time, I might want to FOIL this out and distribute this x. And then this is, yeah, no, there's really nothing that we can do with that. So you can attempt it, and then let's talk about it more tomorrow. All right, next part is going to be the derivative of exponential function base e. My favorite function, because the derivative of e to the x is just e to the x. All right, and the reason why that derivative of e to the x is e to the x is because, remember, derivative means slope. So the slope of this function changes the same as the function. So here, if we had, our slope is going to be a negative, it's a negative slope. No, I don't know why I just drew it like that, my bad. That is not e, right? So e looks like this, and it crosses through e. So here the slope is going to be close to 0. So if I had to graph the graph of a slope, at this point right here, it would be close to 0. At this point right here, it is increasing, right? And the slope, if you think of just the slopes at each point, they are increasing little by little. So the graph of the function e to the x is equivalent to the graph of y prime. And that's why the function e to the x has the same, is the same as its derivative. So now when you have to apply the chain rule, when there's other things other than x in there, we're going to do e to the stuff times the derivative of stuff. So in this case, this guy is being raised to 2x to cubed minus 3x. So when you take the derivative of e to the stuff, it's just going to be e to the stuff times the derivative of that stuff. Okay, remember, this little apostrophe right here means derivative. So I'm writing this out so we can have steps. You don't need to write that. You can just do the derivative as you go. So our final answer would be e to the 2x minus 3x times 6x squared minus 3. And that's it. We would be done. Now, e to the 1 over x. Okay? The first thing I'm going to do is I'm going to rewrite this in a second. Okay? Well, let's do this. E to the 1 over x, its derivative is going to be e to the 1 over x times the derivative of 1 over x. Now, 1 over x, when you rewrite it, it is going to be x to the negative 1, right? So we're taking that derivative. So let's take the derivative. That means we bring down that negative 1. So we got e to the 1 over x times negative 1 x to the negative 2. Clean it up. Bring the negative to the outside. And that x to the negative 2 down. And that's our answer. All right, so we do have a few additional rules that we have to talk about. If a is a positive number not equal to 1 and x is any real number, then the exponential function to the base a is denoted by a to the x. So this is not e to the x, but a to the x. And a to the x is the same thing as saying e to the ln of a to the x. Because e and ln, we will learn, will cancel each other out. And you're just left with a to the x. Another rule is for log base a of x. And that can be rewritten as using the change of base formula, where you can rewrite log base a of x as ln of x over ln of a, or something like this. So I prefer this one, ln of x over ln of a. So you break up the x and the base. And if you actually put this into the calculator, you'll see that this function and this function will be the same. Now, when you look at the derivatives for bases other than e, all right, the derivative of a to the x is ln of a times a to the x. These are just things that you do have to memorize. And if x is not just x, if it's an actual function, you have to remember to take the derivative of that function. And then the derivative of a log base a of x is always going to be 1 over ln of whatever this base was times whatever this x is. And then, of course, if the x is a function, you got to take the derivative of that function. So here's an example. This is the base a. So this is similar to a to the x. And its derivative is just going to be ln of that a, in this case a is 2, times 2 to the x. And that's it. Okay? Because this x is just x, its derivative is 1, so we don't have to write that down. But here, the function, the u is going to be 3x, right? So this is in the form a to the x. So its derivative is going to be ln of the a, which is 2, times 2 to the 3x, times the derivative of u, which is 3x. Right? That's my u. So it's going to be 3 ln of 2 times 2 to the 3x. I just took the derivative of 3x, which is 3, and moved it to the front. Next is if you have a log and the base is not e, that means it's not ln. This is not ln of cosine of x. So this is another one that you just have to kind of commit to memory at this point. But the y prime is going to be 1 over ln of a. In this case, ln of a is 10. So 1 over ln of 10 times the x part, or the u part, which is cosine of x. But of course, you cannot forget to derive the derivative of the inside function. And that's going to be the derivative of cosine of x. So we end up with the derivative of cosine of x is negative sine x over ln of 10 times cosine of x. Last example, chain rule, differentiation using data tables. So when you're given data tables and asked to differentiate, you want to rewrite things out first before filling in tables. So the values of two differentiable functions, f and g, along with their derivatives, are given in the table above. So let's answer the following. So if you had to figure out h prime of 2, first thing I'm going to do is I can see that this is a composition function. Composition function, you need to think of chain rule. Whenever you have a composition function, you're going to take the derivative of the outside first, right, with the inside stuff following. So it's going to be f prime of g of x times the derivative of the inside. And now we're going to plug in that 2. So f prime of 2 times g prime of 2. And we should have all of this information from the table. So g of 2, because we need to start inside the parenthesis. So g of 2 is 3. So f prime of 3 times g prime of 2. And now f prime of 3 is negative 1, and g prime of 2 is 3/2. So f prime of 3 is negative 1 times 3/2, so our final 3/2. All right, I'm going to leave part B for you to do, and we'll talk about this in class tomorrow. And that's it for section 3.1. Good luck.